Now let's welcome our next speaker, Professor Pu. Professor Pu is a professor in the School of Civil Engineering, Civil and Hydraulic Engineering at the Huazhong University of Science and Technology. His research interests cover waste disposal and contaminated, coupled flow and contaminated transport in deformable porous media, geoenvironmental remediation, etc. Today, his topic is rapid treatment of hydraulically dredged mud slurry using vacuum-assisted fabricated horizontal drain. Let's welcome Professor Pu.
Thank you, Professor Gu, for the nice introduction. And I also want to thank Professor Si and Professor Tang for giving me this opportunity to present my work here. Can you hear me clearly?
Yes, perfectly.
Okay, great, thank you. My presentation today is on rapid treatment of hydraulically dredged mud slurry using vacuum-assisted prefabricated horizontal drain. So in this presentation, I will use the abbreviation PhD to refer to prefabricated horizontal drain. This is my presentation outline. First, I will give some background information on mud slurry, and then I will present several methods that are used for mud slurry treatment. The first one is PhD-based vacuum preloading method. The second one is PhD-based vacuum flocculation combined method. And the third one is PhD-based vacuum solidification combined method. All of these three methods are similar. They all use PhDs to facilitate the vacuum preloading. And lastly, I will also introduce a computational model that we developed to predict the behavior of PhD vacuum-induced consolidation. So first, some background. Each year, a huge volume of dredged mud slurries are produced worldwide due to different kinds of dredgings in aquatic environments, for example, in lakes or in rivers, in ports, in reservoirs, and in seas. And it is estimated that about several 100 million tons of such slurries are produced each year. So it's a huge volume. And the dredging can be for different purposes. Some is for instance, the deepening or widening of navigational channels. Some is for environmental remediations. Anyhow, there are lots of dredgings going on, and they produce lots of waste slurry. And these dredged mud slurries exhibit poor engineering properties. For example, it has very high water content. Usually the water content exceeds 200%, and sometimes it's higher than 300, 400, or even 500%. So it's several times the liquid limit. So it's actually in a slurry state. So it's not really a soil, it's more like a mud slurry. It's more like liquid. And because of its high water content, it's usually in a loose state. So it usually has very high compressibility. From the figure here, Professor Morris compiled lots of data for different kinds of dredged materials. We can see that the compression index, CC, usually range between 0.8 to about 2.0, and sometimes it's even higher than that. In contrast, we can see that in conventional soil mechanics, if the compression index CC is higher than 0.4, then we consider it as high compressibility soil. So you can see here the compressibility of mud slurry is usually at least 2 times that. And also because of its high water content, it has very low bearing capacity. It usually, the bearing capacity is lower than several kPa, usually lower than 2, and sometimes even negligible, and cannot be measured using conventional testing equipment. And also, because of uncontrolled release of polluted water into the aquatic environment, more and more frequently, those mud slurries contain contaminants. For example, such as heavy metals, organic compounds, or nutrients such as nitrate or phosphorus and others. So we have this kind of high water content mud slurry. The best way to handle it is to come up with some treatment methods and transform the mud slurry into some kind of materials for beneficial reuse. For example, we can turn it into fill materials for construction, for instance, embankment or levees or dams, etc., etc. We can also make some brakes for pavement, for example, and also people have tried to make it ceramicides. And the key for the treatment here is how we can reduce the water content effectively and efficiently. And there are many methods out there to treat the high water content mud slurry. One commonly used is the prefabricated vertical drain, the PVD based vacuum preload method. This method has been used many years in the field of conventional geotechnical engineering for soft ground improvement. And more recently, people have started to use it for mud slurry dewatering. So the idea is simple. We simply insert the PVDs, the vertical drains, into the ground, and then connect the PVDs with vacuum pumps, and then we apply a vacuum pressure, and then the vacuum pressure can suck out the water and reduce the water content. And overall, the PVD-based vacuum preloading method is economic and effective, but still there are many issues that need to be solved when using PVDs. The first issue is that, as I mentioned earlier, the mud slurry has very high water content. That means it has very low bearing capacity. So, in the very beginning, the personnel and the equipment cannot access the construction site. They may even sink into the slurry. So usually there is a very long, time-consuming pre-treatment before those those vertical drains can be inserted into the ground. The pre-treatment include sun drying or sometimes sulfate deposition or consolidation, depending on the method used and depending on the scale of the site, the construction site. The pre-treatment can be very long, sometimes months or even years. Another issue is that the PVDs can be severely bended because the mud is very soft. After the treatment, after the consolidation, there will be a significant deformation, and because of that, the PVDs will be severely bended, and that can cause a decrease in the transfer of vacuum pressure, and therefore a decrease in the dewatering efficiency. So later on, people began to use the PhD-based vacuum preloading method for mud slurry treatment. Conceptually, it's easy. Just replace the vertical drains, the PVDs, with horizontal drains, the PhDs. First, let me show you the procedures of the PhD-based vacuum preloading method. So first, we need to lay the first layer of PhD at the bottom of the disposal site and connect the PhD with drainage tubes and with vacuum pumps. And then we fill the mud slurry into the disposal site and then start the vacuum preloading to dewater the slurry. And after that, we lay the next layer of PhD, and after that, we continue to place the mud slurry into the disposal site and then start the vacuum pump to pump out water. So we repeat this process over and over again until osmotic slurry is placed into the disposal site. So conceptually, it is easy. We simply replace a vertical drain with horizontal drain, but the benefits are as follows. First, the PhDs are placed before the mud slurry is filled into the disposal site. And because of that, the time-consuming pre-treatment is no longer needed. That alone can save months or even years of time. And secondly, because the PhDs are placed earlier, we can do the filling and also the dewatering of the mud slurry simultaneously. Namely, as we place the mud slurry into the disposal site, we can, at the same time, we can dewater the mud slurry, so we don't need to wait. And because of that, the overall dewatering efficiency is significantly increased. And thirdly, when we use PhDs, the horizontal drains, we will not have significant bending because the drain board will settle together with the soil, with the mud. And therefore, the vacuum transfer efficiency of PhD will be better than that of PVDs. And lastly, during the process of filling of the material, we can also mix in additives into the mud slurry for improved treatment efficiency. For example, we can add in flocculant to improve the dewatering efficiency. We can also add in solidifiers such as cement binder to increase the shear strength. First, we will conduct some small-scale model test to demonstrate that the PhD have better dewatering performance relative to PVD. So we have two model boxes. One has a PVD in the center placed vertically, and then we have another model box in which we have a PhD laid horizontally in the center. This is the test procedure. So we mix the slurry, and then we place the slurry into the model tank, and then we start the vacuum pump. And after the model test, the slurry is turned into soil. So we take out the soil sample for other type of tests, such as strength testing. This figure shows the shapes of the PhD and the PVD as a drain board after the model test, after the dewatering, the whole dewatering procedure. On the left, we can see that the red curve, which is a drain board, we can see that it is severely bended. And on the right-hand side, the PhD was still, the bending was negligible. It's still pretty much flat. And the yellow curve is the soil surface after the treatment. We can see that the soil surface for the PVD was significantly uneven. We have a very uneven surface, which means the treatment will be also uneven. On the right-hand side, the soil surface was much more even relative to the case on the left. We'll also look at the average water content for the model tests with PhD and with PVD respectively. We can see that for the PVD, which is a red curve, the average water content of the slurry decreased from initially 270% to eventually 110%. And for the PhD, which is the blue curve, the decrease of water content is more significant. The final water content is only 60%, which is roughly about 1/2 of that for the PVD. So we can see that the dewatering efficiency of PhD is much higher than that of PVD. Later, we also use this PhD-based vacuum method and combine this with other types of like chemicals, for instance, combine this with flocculant. This is a part of the model test program. We have 6 different groups of tests with different APAM content. The APAM is short for anionic polyacrylamide, which is a common type of flocculant that has been commonly used for water treatment. And in recent years, people have also began to use this for mud treatment because this APAM is a polymer material. They have very long chains, and these long chains have bridging effects that can bring all the small particles together and to form large flocks. And when you have large flocks, those large flocks can make the soil particles settle much faster, and also you will have a larger pore size, which means the water can flow through the soil more easily. And because of that, when you combine this with vacuum, you have much easier dewatering effect. So this is the height of soil versus time. We tested different contents of flocculant versus no flocculant. So on the top, the natural settling, this curve, the depth curve, that's for the case without flocculant and also without vacuum. So it's all natural settling. This is what happens when you place the mud slurry into a disposal site without any treatment. As you can see in this case, the slurry settled very, very slowly. It took about 400 hours to have a 50% deformation. So the height went from originally 40 centimeter to finally 20 centimeter. That whole process took about 400 hours. In contrast, if you look at the red curve, in this case we added in the vacuum pressure. In this case, the dewatering process is significantly increased. You can see that it took only about 100 hours here to reach 50% deformation. And on top of that, if we further add in the flocculant, we can see that the dewatering process is further increased. In general, the slurry settled faster for increasing APAM content. So overall, we can see that the proposed method gave faster, not faster settlement, but also larger magnitude of settlement. In addition to the dewatering efficiency, if we look at the strength, adding the flocculant and the vacuum pressure, that also can increase the shear strength significantly. We look at different flocculant. On the left, we have used APAM. On the right, we used APAM and also lime, some kind of composite flocculant. So on the left, we can see that the shear strength of soil first increased with the APAM content from about 15 kPa to 43 kPa. So that's about 2 times increase because of the bridging effect of the flocculant. And after some point, the strength will decrease with further increase of flocculant because the flocculant is some kind of polymeric material and has high viscosity. And on the right-hand side, on top of APAM, we further added in lime because lime has both the effect of flocculant and the effect of binders. So when we're adding both flocculant and lime, the strength can be further increased. So for the highest one, we can have 60 kPa of strength. So in section 4, I will present some PhD-based vacuum and solidification combined method for mud treatment. In this case, so on top of the vacuum preloading, we add in a solidifier to further increase the strength. This is the mud slurry that we use. In this section, we test both clean mud and also contaminated mud. For the clean mud, we primarily look at the dewatering efficiency and the mechanical behavior, such as the shear strength. For the contaminated mud, on top of that, we also look at the stabilization effect of the heavy metals. This is a test procedure. So again, we first mix the slurry and place the slurry in the model tank. Then we start the vacuum preloading. And after that, we take out the soil sample and cure the soil samples in a curing chamber. And after that, we take them out for other testing. This is the model test program. We have three series of tests. In the first case, we use direct solidification. In this case, the mud slurry was solidified at a very high water content without prior dewatering. So as you can imagine, it will have very low strength after the solidification. At the bottom, we also have the PhD vacuum preloading method. In this case, it has no binder, just vacuum preloading, same as in section 2 of my presentation earlier. And in the middle, we have this PhD VPS method, which is a PhD-based vacuum solidification combined method. In this case, we kind of combine the one on top and the one on the bottom. And we test the different initial water content of the slurry. We test the different magnitude of vacuum pressure and different vacuum preloading duration, and also different semen content. But due to time limit, I'm not going to present all of them. So this is average water content versus time for different treatment methods. The black curve on top, that's the direct solidification method. As you can see, the reduction of water content is very small. It went from 300% to 270%. That's because some water is consumed by the semen. And in the middle of the red curve, that's for the vacuum preloading method. In this case, there's no binder, but there is a vacuum that sucked out the water. And because of that, the water content reduced more significantly from initially 300% to roughly 200%. So the dewatering efficiency is higher than, is better than direct solidification method about here. And most interesting is the PhD VPS method. In this case, the average water content reduced even more significantly from 300% to 140%. And more interestingly, you can see that the blue curve drops much more faster than the red curve. That means the dewatering efficiency is improved significantly. And the reason for that is the change in the microstructures. We tested the coefficient of permeability for the soil without a semen binder and with semen binder. You can see that in the early times, when you add in a semen binder, the coefficient of permeability is increased. That's why you have a faster dewatering efficiency in the earlier figure. The increase of permeability is attributed to the fact that the semen's hydroreaction at early times has effect of flocculation due to the generation of calcium ions, and also the hydrates have some skeleton building effect. It pulls the particles together and increase the pore size, and because of that, at the very beginning, the dewatering efficiency can be improved for vacuum preloading. And because of that, the mud is solidified at much denser state later on. We'll also look at the unconfined compressive strength. On the left, you can see that the direct solidification method without prior dewatering. We tested different initial water content, and you can see that the strength, solidified strength, decreased significantly with increasing water content from 200% to 400%. So this tells us how important it is to lower the water content for further treatment. So on the right-hand side, we have a comparison between direct solidification method with the proposed PhD VPS method. You can see that for initial water content of 300%, the direct solidification method only has a final strength about 10 to like 15 kPa, and on the right hand side, with the PhD VPS method, the treatment, the strength after treatment can be as high as almost 90 kPa. So the strength can be increased by more than 5 times, sometimes even 10 times or even 20 times, depending on the initial water content. We also look at the MIP test to look at the pore size distribution.
Professor Pu, we have 2 minutes left.
2 minutes?
Yes.
Okay.
2 minutes.
Okay. I will accelerate. So you can see that after the treatment with the proposed PhD VPS method, the pore size was significantly reduced. We have less large pores and have more small pores. That explains why we have significantly increased shear strength. This is the SEM results. I will skip this because of the time limit. We also look at different binder types. We compared the traditional cement binder with the alkaline activated GGBS, which is a granulated plasfluorine slag. We use different types of alkaline such as lime, MgO, magnesium oxide, and carbide slag. The alkaline activated GGBS have better performance than the traditional cement binder in terms of both strength and the environmental effect. And the previous presenter, Professor Yao Lin, has done a lot of good work on this topic. This figure shows the mass of discharged water, and the blue curve is for the cement as a binder, and the black curves are for the lime activated GGBS. And you can see that more water was sucked out. The mass of discharged water can be increased by 50% when we replace the cement binder with GGBS binders. And because of that, the strength was also increased significantly. On the figure, you can see that the proposed PhD VPS method gave much higher strength than the direct cement solidification. The increase is about 10 to 60 times. And as for the binder, the lime GGBS binder gave also much higher strength than the cement binder. The increase is about 4 to 11 times. So in addition to the clean mud, we also look at the contaminated mud to look at the to look at the stabilization effect. I will go quickly here. So here, this is the leaching concentration of heavy metal zinc, and you can see that for the direct solidification, that has the highest leaching concentration. And then when we use the PhD VPS method, that can reduce the zinc concentration by about 50%. So a significant increase in the stabilization effect. The reason is that it caused the change in the speciation of heavy metal. When we treat the mud slurry with PhD VPS method, especially when we use the MgO and GGBS as a binder, there are less unstable fraction of heavy metal and more stable fraction of the heavy metal. And lastly, I will present some computational model that we developed for PhD-induced consolidation. Because when we use this PhD-based vacuum method in the field, we need to decide how we design this PVD, how long we need that, and what is the lateral spacing and a vertical spacing of the PhDs, especially when we have complex conditions such as layer soil profile, and etc. We need to design this whole thing. We need to have a tool to analyze the change of water content, the change of the sediment, and etc. So we need to have a numerical model to analyze the deformation process. We developed a model, and then we validated this model by comparing with other analytical solution, and also with numerical model, and also compared with a large-scale field test conducted by Shisha back in 2014, and again the numerical model performed well with the field testing data. My presentation was pretty fast, so here's a list of my publications on this topic. If you're interested, you're welcome to download and read. So that's all for my presentation. Thank you very much.
Okay, thank you very much, Professor Pu. It's a very nice presentation, but unfortunately we don't have time for questions. So I'm sorry, we have to move on.